Hi guys, I'm Chris Bowden and welcome to the Geek Group. In this week's Equipment Autopsy, we are taking apart a transmitter. Now this isn't like the kind of transmitter like you'd think like with RadioNet. This is a piece of avionics equipment. It's for in probably a very large airplane. This is the transmitter side for the how much gas you're using per rate of time gauge. It's kind of like a gas gauge, but instead of measuring how much fuel is in your tank, it's how much you're using. And if you look here, you can see this is the transmitter. The receiver would be the gauge in the cockpit. And this transmits the rate of flow for fuel in a range of 50 to 45,000 pounds per hour, which is a hell of a lot of fuel. So it's kind of cool. Now, this is our third attempt at making this video because this thing has been a bit of a pain. So instead of watching me take out all the bolts, some of them are already out. We've kind of, it's like when Julia Child just reaches down and, hey, it didn't take me 6 hours to cook that turkey, it's done. This is that kind of thing. So there were 4 bolts here. It wasn't anything terribly exciting. You didn't miss much, okay? But we got it. It's there. So let's take a look at what we've got just from the outside. Here's the cover. Now there's 2 of these plates on top. You can see there's one over here and one here. Now inside we've got a little 2-pin socket held in place with safety wire that holds in the bolts. Safety wire is something you'll see a lot in danger places. You see them a lot in aircraft and stuff like that. It's a way of making sure that the screw is never going to come out on its own. Because if you have this thing's probably mounted on the side of a jet engine or something, so there's a lot of vibration and there's heat and expansion and then it cools off and it contracts and everything's moving around. You really don't want your screws to just start falling out. So they use safety wire to keep them in. And we'll take a look at that real quick. I'll remove these screws. I'll do it over on this panel because this one's still screwed in. It's the same thing. This plug has 3 pins on it, but you can see the safety wire around the top. Now I'll just cut this like that, and we'll just cut the wire right off. Now we'll pull that wire out, and you can see, we'll unscrew it a bit. Wow, this is kind of manky. Slide the wire right out. And I'll pull this bolt out, which is more than a little bit oxidized. Here, I'll turn it around like that so you can see. Now, if we look really close, you can see inside the head of the bolt, see that little hole? And there's one out, that one's even easier to see. Look at the nice shiny bolt right there in the corner. See the little hole right through it? The safety wire goes right through the hole, and then you tie them together, and now I've got some of the brown goop on my finger. You tie them together, and one can't turn with it tied in place. They're not anchored to the thing. Sometimes, like with a castle nut or something like that, the nut will be anchored to the bolt with a pin through it, like a cotter key. This is a little different. These are tied together so that's its frame. This one can't come out because that's there and it's anchored there, so they kind of hold each other in place. So we've got that. Now, we've also got a date on here that you can see, April 15th, 1969. So this is an older model. Let's pop it apart. And then we can look at the 2 halves individually. Now, on this side, in there, oh, that's cool. That's really cool. Is that held stationary? Huh. This has what appears to be turbine blades, and it's free spinning. It actually rides on the other side. There's a little pin here. I'll turn an angle so you can see it. And these are stationary. And this, I think that's how it works. I think what it does is, all right, let's look at the whole system. I'll see if I can get this apart and slide them out so it'll make more sense, but we're going to want to dig down into each of these. It's going to take some delicate work here, but I'll see if I can do it. Now I'm taking off, so you guys can see, there's two nuts on top here, very thin nuts set up. This is the jam nut. It's the second nut on the shaft. And if you look around it, you see these little bolts sticking way out? I'm pretty sure, if you look at them, you can see there's one here, two here, none here, and one there. And these move up and down. Those are counterweights to keep this very, very balanced. Those are for fine adjustments. Take that off. And if you look down here, you'll see there's another couple, and I'll turn this so you can see. Those are counterweights. Slide that right off. Okay. Now we've got this, which is a very finely balanced propeller. Okay, well, an impeller. So this has straight blades on it, though. All the blades are straight. Okay, we're going to come back to that. Now that we're down in there, you can see this whole thing mounts on a spring. And that spring turns it like that. It's a coil spring. So the spring is set so that the farther I go this way, the more tension it's under. It'll work backwards, but not very much, and there's a damper here on another spring below it. And you can see down under, you can see the other spring moving. So this wants to turn around, and both springs wind the same direction. So when this comes around this way, it adds another level of push on it, of resistance. Now, I wonder how much more we can get out of there. I think that's about it. Let's try. That is exactly the screwdriver I need for this. This is actually cooler than I thought it would be. Okay, I've got the 3 bolts out. That should be what holds that in. At least I think it is. Take the 3 washers out. No, it's staying in there. All right. This end, and we're going to check on this side to be sure, but I think I've got this figured out. This end, as this gets pushed around in there, this mounts on this shaft, and this shaft is allowed to pivot. But as this turns around, it turns the shaft, and the more it turns the shaft, the more force is required to the more force that gets applied to this, the more it turns the shaft. And this has a little sending unit here that is sending the position of this shaft. So this is that side. Now this side doesn't turn, but this side makes that side turn. So this is where it gets weird. That's the rotor. This is the stator. I'm going to pop this off, and I'll bet when we take this turbine out on this end, the impeller, like see how this one is straight right across? I bet when we take this one out, they're bent. They're all twisted around. That's my hypothesis. Oh, I was wrong. I was totally wrong. These are straight. And it gets even weirder. Ooh, look down in there. Look at the gears. I was not expecting to see that. Huh. Okay, this is See, what I thought it was this introduced a spin in the fuel as it went by, and the more fuel that goes by, the more this gets moved, and that was how it measured it. But it doesn't appear to work in that way by using it through an impeller. So let's figure this out. I like it when I'm wrong like that. I like it when it's hard to figure out. There's nothing wrong with being wrong. There's even nothing wrong with being wrong on the internet in front of a whole lot of people. It's how you eventually get around to being right. But that's a cool thing about this. I've never seen one of these before. You probably have never seen one of these before, so this is science. You look at a box and you see certain parts, and you can kind of figure out how that part goes together with that part. And as you get better, you're working out these clues from context, and you can look at it and put all the pieces together and say, well, I know this part works against this part in this way, and this part works with this part in this way. And you can put systems together, and you put enough systems together, and you can figure out what the whole thing does. And that's the fun of an equipment autopsy, is we're just exploring this, because we have no idea. We're just in it. We're just checking it out. All right, so I got those 3 outer screws out. I'm trying to move the whole thing, because I can see, here's where I'm talking about that systems thing. You can, maybe I can get a bright light in there so you can really see it. If we look down in here, this plate right here, you can see how that has to bolt down into the outer tube. So to take this inner bit out, I have to take that screw out. And see, that's one piece onto the next. I want to get that out of there, and that is really serious about being in there. Maybe I can move it a little. It's not very common in the world of avionics to have to force something, and it makes me very uncomfortable to have to do so. But for the life of me, I can't see anything other. Because when you look through it, you can see light around it on all sides. The center module just floats. There's 3 spars that hold it in place, and there's no other bolt holes. This is all just a cast housing. So those 3 screws have got to be how that goes in there. And I'm thinking there's an electric motor down in there. And if I can get to that electric motor, I can figure out what it wants, and I can spin those gears and I can make that move. But I didn't want to have to take the whole module apart to do that. I wanted to be able to pull it out as a complete subassembly. And I fear that if I just take out these 3 bolts, it won't work. It might, so I'm going to give it a shot. But I don't think these 3 bolts are going to get me what I want. I think they're just going to take that out. Yeah, that's just that pin. All right, let's put that back. It's a really precision fit. It's not quite an interference fit, but that's in there with like maybe 5/1000ths of an inch space. The hole it goes into is about 5/1000ths of an inch bigger than the pin itself. It's really well machined. You got to understand, they built this in the 60s. Today that wouldn't be a big deal, but back then, it's serious business. Oh, did you see that? It moved. Whole thing just moved. And if it'll move a little, it'll move a little more. Yep. Okay, I can turn it. I can wiggle it. Okay, hang on, let me get right down in there, because I want to save as much of that cord. Wow, that's really hard. I want to save as much of that cord as I can. Okay. So let's look down in there. You can see it's having a little trouble focusing. I'll put a finger in there. It'll help it out. All right, you can see down in there. So that's just empty. So if got that figured out. Now this holds that on there. Oh, okay. The shaft isn't what moves it. See this little gear that we didn't really pay attention to out there? Well, look, on the inside of the rotor, there's a gear. So when I put that through there, you can see the little gear here lines up with the gear in there. And that locks it right up. And this motor wants probably 400 cycles. All right. Put it right here so you guys can read it at home. Now let's see what this motor tells us. It tells us the frame. We'll clean this off a little bit. The frame is a 17. That's really hard for you guys to read, isn't it? All right. And the model number is 100900. It's rotation, I think that's what that's trying to say. Yeah, it's really hard to read on the camera. The rotation is counterclockwise. The volts is 115, which is a nice, common, easy to use voltage. Frequency is 400 cycles per second. Now they do, on airplanes, they use a lot of AC at high frequency, 400 cycles per second. Regular house electricity in the United States is only 50 hertz. In most of Europe, it's only 50 hertz. So it's 50 cycles per second. So this is at a much higher frequency. And the reason they do that is for things like transformers and all that, which in most electronics, the heaviest part of the thing is the transformer. Well, as the frequency goes up, the size of the transformer can go down to deliver the same amount of energy. So that makes life easier because they care about weight on airplanes. It's kind of important. It draws, is that a 2? No, it's a 3, 0.36 amps. And this is kind of cool. 0.006 horsepower, 6 thousandths of a horsepower. And the RPM is 8,000. Continuous duty, used with an external 0.35 microfarad capacitor. And what's that bottom number? Bottom number says Avian 1116-9-5. So this motor on 115 volts spins at 8,000 RPM. I wonder, and it's rated for 115 volts. So just for kicks, because I don't have a 400 hertz power supply handy, I wonder if it'll work. Now we've got white, green, and blue. I'm going to say with only 3 wires that green is ground, white is neutral, and blue is hot. So I'll grab my Leatherman, which has a really nice set of strippers built into it. I'll strip this wire down. This is really expensive wire. This is expensive wire by today's standards. It's got Teflon insulation. Let's see if we can make this work. And if we can't make it work, we can guarantee it'll never work again. So, now, don't try this at home. It's crazy stupid. But I'm just going to strip these 2 leads. Twist them down tight. Do I have a set of test leads? I'll bet I do. I've got test leads. Do I have test leads that I can do anything with? Oh yeah, that's just what I need. Okay, now here's how to do this in true, massively stupid style. All right. Here's a handy little trick for those of you who are working around stuff like this a lot. Don't ever do this. It's stupid dangerous. You will kill yourself, your entire family, and the girl you take to the prom if you ever try to do this. So absolutely do not do what I'm going to show you exactly how to do, okay? Now, on these leads, you can see right here, they've got these little banana clips, and they've got the little bendy bits that stick out, and there's a little tiny hole through the center of the bendy bit. Okay, you can see you can get in the arch there. So you take your wires. Now we're going to use this as our neutral. So neutral is kind of, that's the the grounded conductor. And we'll just poke that right into there. You get to stick. It's kind of tricky. And this would be a good application for some electrical tape. Yeah! Okay. So you get a little bit of a mechanical connection, but not much. And just flatten this down around it like that. You can take a piece of craptacular electrical tape and just hook that in there. Okay? And if you get the right kind of leads on a good day, you don't even need the tape. The wire will just hold itself in there. So we'll take this one, smooth that out. I'll stick that right in there. Bend it along thing. Stick my tape. Cool. All right, now I got those on there. Now, if this works, which it may or may not, I honestly have no idea. It's science, man. The motor will, since the motor is designed to spin at 400 RPM, or 400 cycles per second input, it's probably frequency dependent to some degree. So the motor either won't work at all or it'll spin a lot slower than the 8,000 RPM it was intended for. Now, looking into a normal plug, you'll see that one's bigger than the other. And we know that our blue wire is probably our hot, so that goes to the red lead. So hot goes to the red lead. Now, when you look into a normal outlet in the United States and you've got the little vertical, it's a face. The little eye is hot. The big eye is neutral. The mouth is ground. Okay, let's try this. I'm going to stick this into hot. I'm going to stick this into neutral. And you got to hold it because just, you got to fight it and wiggle it around. And I'm getting nothing. So I'm going to hold this over here and make sure to keep my skin away from that and squeeze these. Yeah, I'm getting nothing. Yep, nothing, and that's just sad. All right, I'm going to keep this, though, because I have a buddy who works on avionics a lot. And I'm going to see if he can make it happen. And we need a 400 hertz. We need a variable frequency power supply here so that I could just give this 400 hertz. Let's take a look down in here. We've got a neat little, what's that say? S gear? I don't know. So we've got a neat little gear drive here. It's a reduction drive. So this motor spins a lot faster than this does out on the end. Now, I still don't really know how this works, but what I'm thinking is this motor goes on here and spins this. And this sits right next to it like that. And there's a fluid coupling of the fuel. So like, this is in our tube, and we're pumping fuel in this end, and this gets the fuel spinning. And this measures the resistance of the fuel, measures how much, as the fuel flows by, this gets displaced based on how much fuel is in the tube at the time. I don't really know. I have no idea. But it's interesting. And I'm sure somebody out there can tell us more. I know this is a precision balanced wheel, and I know that the meter, the actual measuring part, has to do with how this is displaced. And I know on this side it spins it, and I know fuel comes in one side and goes out the other. And we know from the arrow on here that the fuel comes from this side and goes that way over to this one. So that's my theory of operation. I could be absolutely 100% wrong. I have no idea. But that's my theory, so I'm going to stick with it. All right. You guys have fun. That's it for this week's Equipment Autopsy. I'm Chris Bowden, and you're not. Tune in next week when we autopsy Moose's cat. Until next time, learn more at thegeekgroup.org, where you can sign up, become a member, get involved, and come play with all these fabulous parts. See ya.
This video was made possible by a grant from the Future Girl Foundation.
This video was made possible by thousands of private donations from members and viewers like you. Please visit thegeekgroup.org for more information on how you can donate and become a part of our dreams of Avalon.